In this video, I'm going to do Chapter 6, Number 29, the infamous box problem. Year after year, this particular problem drives my students crazy. The idea is you have a flat piece of cardboard, and you want to cut out squares from the corner, fold up the box as shown here to turn into a box. You then want to calculate the volume of the box, which is simply length times width times height. The trick is you want to calculate the cutout that gives you the maximum volume. This is a classic calculus problem. It's also a good related rates problem, differential equations problem, but we're going to do it iteratively using a loop. Now, the program says prompt the user to enter the area of the flat cardboard. Forget that. It is not wrong. It just makes your life much more difficult. What I'm going to suggest, you input length and width. So you input length, you input width. From there, it's a lot easier to start calculating the size of the box. So you're going to input the length, you're going to input the width. And then from there, you're going to write an algorithm that's going to find the maximum volume. So I've got some code started here. I have some variables, length, width, cutouts, volume, and area. And here's the basic math. When you set a cutout, you have to change the size of the length and the width. Notice how I'm subtracting out the cutout times 2. The reason for that, if you look at that book, the book isn't showing. There we go. If you look at the book, you see how I cut this square out here. I lose 2 squares on the width and 2 squares on the height. Like this, length and width. I lose 2 squares either way. So I'm subtracting those out. And that's what I'm doing here. Length minus equal cutout times 2, width minus equal cutout times 2. Area becomes length times width, of course. Volume is length times width times the cutout. So run this thing. By cutting out 0.1 square inch on the side of the boxes, I end up with a volume of 19.4 cubic inches. I do it again now. Instead of 0.1, let's try 0.2. Run it. Volume is 37. See how it's getting bigger. 3. Run it. Wow. Okay, so we're getting a little bit bigger as we go up. Your problem is you need to continuously increase this cutout until you find the largest volume. So you'll want to do something like this. And the book wants in 3 decimal places. So I have some type of increase to 0.01. I'll set my precision down here to 3, so it looks good. And I'm going to do a simple loop here. You're going to have to modify this loop to find the biggest. So my increment's going to go at 0.01. So this is just going to go 0.01, 0.02, 0.03, 0.04, 0.05, etc. Eventually, my volume will become 0 based on just math, because eventually my cutout will be bigger than the width. I'm not going to care about the area, so I'm going to comment that out. Let's do a run. This is going to take a while. It's going to take forever because it's 0. Equal to 0. Run it again. There we go. That's some outputs. Now you're seeing here, go back to the beginning, volume is tiny. Tiny volume, tiny volume, tiny volume, tiny volume, tiny volume, bigger, 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 bigger. And then we see right around here, I start to slow down, and right here, 6.484, 6.496, 6.5. Right here is my biggest. That's my maximum volume with a cutout of 0.051. Now, that works. That's the logic. What I want you to do is in your code, find that. I don't want you to have to scroll through the numbers and point to it. I want your code to find that biggest value. It's pretty straightforward. You got to hang on to the values of the volume that you calculated in the last iteration and while that. And as soon as you get beyond that, step back a step. All right, good luck.